afternoon is something that's a little bit of an elephant in the room for benchtop NMR. This is the issue of the reduced frequency dispersion due to the lower magnetic fields and the resulting spectral overlap. During the course of the webinar, I'll touch on the differences between high field and benchtop NMR, especially related to the frequency dispersion and the scalar couplings. We'll look at some post-processing strategies that allow you to improve your line shape, particularly the Lorentz to Gauss transformation and the reference deconvolution, and data analysis, chemometrics or multivariate statistics, as a way of looking at the data or treating the data as a whole. And finally, we'll spend some time looking at 2D NMR methods, that's correlation spectroscopy, J-resolved spectroscopy, and total correlation spectroscopy, TOCSY. A traditional high field system, well, these have been around for some time now, and we know they give very high quality data. There is a wealth of chemical information that can be extracted from high field NMR data. This is due to the exquisite sensitivity of the NMR to the chemical environment. The data, if it's collected properly, is quantifiable, and there's a straightforward relationship between the concentration of your sample and the NMR signals. But generally, the high field NMR is carried out at 4.7 Tesla, a frequency of 200 megahertz plus. But there's some downsides to this. Firstly, they usually require specialist facilities for the instrumentation. The instrumentation itself is expensive. There's regular liquid nitrogen, liquid helium cryogen fills to be carried out, and you usually need some sort of expertise for carrying out experiments. By contrast, a benchtop NMR such as Pulsar, we use permanent magnets as for the magnetic field. This doesn't require any cryogens because there's no cooling and provides affordable instrumentation. In addition, the magnetic field, 5 Gauss stray field, is contained within the case, the magnet case, and the footprint is such that it can sit on the laboratory benchtop. So there's no need for a special laboratory. In addition, we have easy-to-use software that makes the acquisition of NMR data easy, so you don't require an NMR expert. But that's not to say that we hide away the operation of the spectrometer and use it as a black box. It still allows a full spectrometer experience to students. We use standard 5mm tubes for the samples and the spin flows we've mentioned to acquire the data. This data is then exported seamlessly into MNOVA software, where you have all the standard processing tools for your NMR. So let's start by talking about the ubiquitous ethyl crotonate, and many people who have worked with NMR will know this molecule very well. If we plot the spectrum of ethyl crotonate in frequency, we can see that at 60 megahertz, in comparison to 300 megahertz, the spectrum looks quite compressed. And this is due to the frequency generated by the magnetic field. But this is a problem that's been known in NMR since its inception. And the solution is to use the units of ppm. In ppm, we take a frequency, subtract a reference frequency, and divide by the spectrometer frequency. So that's the frequency of our spectrum in hertz divided by the spectrometer frequency in megahertz. And when we plot those spectrum in ppm, we find that all the resonances in the 300 and the 600 now line up. But there's still a notable difference between the two spectra. And if we zoom in on the quartet, we can see that in the case of the 60 megahertz spectrum, the peaks firstly seem much broader. This is despite the fact that they have exactly the same line shape. Additionally, a 6 Hz coupling at 60 megahertz is 0.1 ppm, as opposed to the 300 where it's 0.02 ppm. This is a direct result of the fact that the J coupling doesn't scale with the magnetic field, unlike the chemical shift. And as such, the spectra can appear a little bit broader, but also with the J coupling further apart, this can result in some overlap. Another difference between the high field and the low field spectra is strong coupling. If we take a pair of spins mutually coupled with a 10 Hertz coupling, we can see that if the frequency difference between the two is 100 Hertz, we get 2 doublets for each of the spins. If this was a signal at 300 megahertz and we were to collect the same spectrum at 60 megahertz, where the frequency has now been reduced by a factor of 5, we can see the shape of the spectrum becomes slightly different and we have significant roofing on the spectrum. This is a result of the strong coupling. There's nothing wrong with it, but actually in 60 megahertz spectra, you often see this kind of roofing effect. If we take things to an extreme and we reduce the frequency difference between them further, we can see that there could be some confusion between a quartet and the two doublets. And when the frequency finally becomes 0, we can see that the whole system collapses into a single peak. But having said that, and having highlighted these differences, many spectra that you can collect at 60 megahertz are absolutely fine. Here's a spectrum of ethyl crotonate, and we can clearly identify the ethyl group, the CH3 triplet, and the CH2 quartet. And at the other end, the crotonyl group, if we zoom in, we can see the doublet of doublets that's associated with the CH3 group of the crotonyl group, and the 2 doublet of quartets associated with the olefinic group. But we'll now talk a little bit about some of the post-processing methods that we can use to enhance our line shape. The first is the Lorentz to Gauss transformation. And in this, we will apply a filter in which we try and cancel the natural decay of the time signal with an increasing exponential. Unfortunately, when we do that, we can see it has a catastrophic effect on the noise. We can also apply a Gaussian decay, and we can see that that smooths and slightly changes the shape of the signal. Combining these two together, the combined filter gives us processing that changes the shape and gives slight enhancement to the time signal. Applying a Fourier transform to that, and we can see what's happened is the line here, originally half a hertz wide, in red, has now been narrowed at its base, still half a hertz wide at the half width. The reason for this is the transformation has converted the Lorentzian line shape to a Gaussian line shape. A Lorentzian line has wide wings at its base, the Gaussian is much narrower. So this is one way to try and enhance the line shape and minimize overlap. But caution is advised with this, because as we can see, if we try and narrow the lines too much, and here we start with the same 0.5 hertz half width line, and we try to narrow it to a 0.2 hertz half width in the orange, we can see that by trying to narrow the line, we've increased the noise significantly in that spectrum, but we've also introduced some artifacts where the lines appear to be split. So care should be taken when applying this. Reference deconvolution is another common method. In this, we select either an internal or external reference, and we use that as a reference line shape. That line shape is then corrected and applied across the whole spectrum. And here we can see from the overlapped region how the lines have been significantly narrowed, and many of them are resolved down to the baseline. Given the frequency dispersion of the benchtop, the use of the Lorentz to Gauss transfer or reference deconvolution is pretty much a no-brainer. However, increasing the spectral resolution and line shape with post-processing methods will also increase your noise in your spectrum, and as we've just seen, can result in some artifacts and line distortions. Although excellent resolution and line shape can be achieved with a combination of shimming and post-processing, there are still examples where overlap of the multiplets mean these can't easily be resolved. And a good example of this, which has been of particular interest in the food industry, are triglycerides. So what is a triglyceride? Triglyceride is made up with a glycerol backbone and 3 fatty acid chains. the fatty acid chains may be saturated, they contain no double bonds, monounsaturated in that they contain a single double bond, or polyunsaturated where they contain multiple double bonds. And if we look at the 500 megahertz spectrum of a typical oil, we can identify, for instance, the glyceride backbone. Here's the signal from the 4 beta hydrogens on the backbone. We can identify signals from the olefinics. We can identify the bisallylic, that's a CH2 next to a single double bond. We can identify a bisallylic, which is a CH2 sitting between 2 double bonds. We can also identify the CH2 next to the ester coupling, and we can also identify the terminal CH3. The other peaks are related to the other CH2s in the spectrum. If we consider the same spectrum at 60 megahertz, we can see there's considerable more overlap. However, despite the overlap, we can still identify the key signals from the same functional groups. Here we have the same glyceride backbone, the signals from the olefinics, the bisallylic peak, and the CH3. But actually, rather than spending time and effort trying to resolve these peaks, we can take a strategy that comes from other modes of spectroscopy, and we can treat the spectrum like a fingerprint. Which brings me to the Horsegate scandal. A couple of years ago in the UK, we had a scandal that horse meat was being substituted for beef in some ready meals. And at the time we were working on a project looking at oils with Benchtop NMR. And it occurred to us that we may be able to see differences in the fats from different types of meat. And a cursory view of the literature very quickly revealed that there are significant differences between different animals and their fatty acid contents. The question was, can we see these differences in a 60 megahertz proton spectrum? And the answer is yes, we can. The beef is low in polyunsaturates, and while we still have an olefinic peak, we have almost no bisallylic peak. Pork has more polyunsaturates, so we see a larger bisallylic peak and a larger olefinic peak. And horse is high in polyunsaturates, and we see quite a strong bisallylic peak and quite a long olefinic peak. So even by eye, with these representative spectra, we can see differences between the different animals. So we set about taking a test set of beef and horse to see if we can use principal component analysis to screen the beef from the horse. And in the first set of data, we collected over 50 samples of beef and horse on 4 different instruments in 2 different labs. And using PCA, we built a model that separated the beef from the horse. Subsequently, we then carried out an experiment using the model from the first set of data to screen beef, pork, and horse to identify the beef from the other meat types. And we can see out of the almost 100 data sets that we had, only 2 beef were misclassified as not being beef, and no pork and no horse was passed through as beef. We can extend this using a different set of statistical tools, in this case partial least squares, to try and do a supervised classification of different species. So here we take our data sets to build the model, and subsequently we run test samples to identify which species of animal the meat has come from. Now, while we did this on meat, because it was topical, this kind of approach is not limited to the food industry or the analysis of fats and oils. The approach is quite general for any problem where you're looking to classify a set of spectra or a set of samples. Having said that, the multivariate statistics are very powerful, but we require a large data set and we require accurate reference data. So it's not applicable in all cases. In the cases where we maybe have 1 or 2 samples and we're looking to confirm a structure or the presence of a certain chemical, we can use more traditional NMR experiments. And in this case, we'll talk about some of the homonuclear 2D NMR. In general, these experiments follow a time series in which there's a period of preparation. That's to say, we generate transverse magnetization, which we're going to manipulate to get our signals. There's a first time evolution period in which we label some of the magnetization with the spin frequencies. A mixing period in which we allow the spin physics to transfer magnetization between different sites. And finally, the direct detection period where we detect our final signal. So a typical 2D experiment would start, we would run through the experiment and collect the first set of data. We then repeat again, this time incrementing T1, collect a new set of data. And we continue doing this with increments in T1 until we'd collected, say, n steps of m time points, creating a data matrix of n times n points. Now, in essence, this data matrix, it's now two time directions. We have T2, which is our direct acquisition, and T1, which is our indirect acquisition. This time data can be Fourier transformed with a 2D Fourier transform to generate our two-dimensional spectrum. Now here we've gone from two time dimensions to two frequency directions, F2 and F1. In this case, the amplitude of the signals, or the height of the signals, is represented as contours and is effectively coming out of the page. The crux of all the 2D experiments is actually the spin physics during the mixing period. So depending on how you prepare the magnetization and what you do during the mixing leads to different signals. The first experiment we'll consider is the correlation spectroscopy, or COSY experiment. In this experiment, we'll follow through by following the timeline in this pulse sequence diagram. And in common with all NMR experiments, the first step is to wait until your magnetization is equilibrated. This is followed with a 90-degree RF pulse. What that does is to generate transverse magnetization, and this is what we're going to work with through the experiment to give our final signals. The T1 period is our indirect time period, the thing that will be incremented from experiment to experiment. And during this time, the spins evolve under their chemical shift, which gives them their frequency labeling, and their J coupling or scalar coupling, which causes the mixing between the spins. A second 90-degree pulse causes transfer of the magnetization from one spin to another, and the final time period allows the spins to evolve with their new frequency. Finally, we rinse and repeat, starting the experiment again, but this time incrementing the T1. So if we return to our friend ethyl crotonate, and we can look at its COSY spectrum, the way to interpret this spectrum is first to look at the diagonal. The diagonal represents magnetization that has not been transferred between two spins, and therefore has the same frequency in both the F1 and the F2 dimension. If we move off diagonal, in this case moving from the CH3, the spin labeled A, we see that there's a cross peak or an off diagonal peak associated with the frequency of spin C. That's to say that in the first time period F1, the magnetization was evolving with the frequency of spin A, but in the second time period it was evolving with the frequency of spin C. And during the mixing time, that magnetization had been transferred from the spin A to the spin C. And we can see the symmetry of the spectrum is such that each of these pairs of coupled spins forms a little square. So here we have spin A and spin C that are coupled together, the ethyl group in ethyl crotonate. And here we have spin B and spin D, spin D and spin E, and we can also see, because of the double bond, that spin B would also be coupled to spin E. But ethyl crotonate is a very well-behaved sample, very useful for showing these kind of experiments, but we want something a little more challenging. So although the 2D experiments for a reasonably strong sample, typically 0.2 molar and better, will require between 30 and 60 minutes, it is possible to carry out the COSY in 3 to 4 minutes. And to do that, we'll take a sample of ibuprofen. Now, again, it's quite a nice spectrum, but I'll draw your attention to spin B. Spin B sits in between two CH3s at A, so that's at least 6 hydrogens that are going to split the signal, and a CH2 at F, so that's 8 hydrogens splitting the signal. And what we can see is it forms a multiplet partially obscured by C, and because of all the splittings, the amplitude is being greatly decreased. So here we have an excellent example of the kind of overlap that we might see. But we can run our quick COSY experiment, taking only 3 minutes, and we can see here the diagonal. But if I zoom in here, what we can see is we've resolved the peak B in the COSY spectrum. And that's because there's no cross peak with C. Spin C is in another part of the spectrum. And in this case, it's a reasonable amount of time, albeit a reasonably strong sample. But what we've managed to do is use the second dimension to separate out the peaks. Now we can move to a second experiment, and in this experiment, we decouple the splitting pattern from the chemical shift. So we approach the separation of the signals in a slightly different way. Again, like the other experiments, we use a 90-degree pulse to create the initial transverse magnetization. In the second period, we allow the spins to evolve under their chemical shift and their J-coupling. But then we apply a 180-degree pulse. The effect of that pulse is to refocus the chemical shift that has happened in period 2, such that by the end of period 4, the total chemical shift has been refocused, but the J-coupling continues to evolve. Finally, we collect our direct time signal, and once again, we rinse and repeat to build up the 2D data set. So returning to ethyl crotonate as our example, we can see now that this spectrum is somewhat different to the COSY. There's no diagonal. The symmetry is actually about the 0 point in F1. And in the horizontal direction, the F2 direction, what we're getting is the chemical shift information. So we can see that all these columns of peaks actually line up with the center of the resonances. And if we look horizontally, what we're actually plotting there is the splitting patterns. So a good example, if we look in here, we can see the quartet of the CH2 is actually represented with the quartet here. And what this allows us to do in this case is to accurately measure the coupling constants for all of this spin system. But once again, ethyl crotonate is very well behaved, so we want to look at something a little more challenging. So here we have 2,2-hydroxyphenyl benzothiazole. Apart from the OH, we have 8 hydrogens, all of which lie in the aromatic region. And we can see, if we zoom in on the spectrum, those 8 resonances have many nearest neighbors, and there's a lot of couplings, and what we end up with is a very crowded aromatic region. And actually, in general, not just in this case, the aromatic region is often crowded because the chemical shift dispersion for the aromatic signals is quite narrow, but because of the benzene ring, there's a lot of mutual couplings. So we can run our J-resolved experiment, and once again, we find in the horizontal direction, we have the chemical shifts, and in the vertical direction, we have the coupling patterns. And what that allows us to do is by removing all the couplings, we can identify the 8 resonances associated with the benzothiazole. We can also take this a step further and consider homonuclear and heteronuclear couplings. In this case, we'll look at 5-bromo-1,2,3-trifluorobenzene. And in particular, we'll home in on the 2-fluoro position. Now here we can see we have a fluorine with 2 fluorines as nearest neighbors, and in fact these are identical. So it has 2 identical fluorines, but it also has 2 identical hydrogens as neighbors. And it causes this coupling pattern. In fact, this is reasonably easy to recognize. We've clearly got a triplet of triplets, 1 large coupling and 1 much smaller coupling. But we can run the fluorine equivalent of the J-resolved experiment, and what we find with that is that the homonuclear couplings are spread out in the F1 direction, and we can measure the 20 Hertz fluorine-fluorine coupling with this. But the heteronuclear couplings are in the chemical shift direction, the F2 direction. And here we can measure the 6 Hertz couplings. So this means that our J-resolved experiment, depending on how we apply it, allows us to separate out both chemical shift and homonuclear couplings as well as the heteronuclear couplings. So far, all the 2D experiments we've looked at have been magnitude experiments. That's to say, the magnitude refers to the fact that the spectra are displayed in magnitude mode. This has a disadvantage that the 2D line shapes in magnitude mode are a mixture of real or absorption line shapes and imaginary or dispersion line shapes. And this results in signals with very broad wings. So it means separating out some of the signals can be difficult because there's interference from the broad base of the signals. 2D experiments can often be acquired in such a way that they can be displayed in pure absorption mode. These are so-called phase-sensitive 2D experiments, and they can improve the resolution. An example of that we'll consider today is the total correlation spectroscopy, or TOCSY experiment. In the TOCSY experiment, we can see that we have an RD period in which we allow the system to equilibrate. And just like the COSY, we apply a 90-degree pulse, followed by an evolution period T1 in which we're labeling the first spins. But in place of the second 90-degree pulse in the TOCSY experiment, we apply a spin lock. And what the spin lock does is to suppress the chemical shift evolution. So basically, we're taking a direction in space and we're locking the spins in that direction and preventing them to rotate away. So the only interaction that allows them to evolve is their scalar or J coupling. Now the advantage with this is that the J couplings are such that they can propagate down a chain. So here we won't just see nearest neighbor interactions, we'll actually see interactions down a mutually coupled chain. The spin lock can be achieved by using composite pulses. The traditional sequences are MLEV17, which was actually used to collect this data, or DIPSY. Finally, we do have our direct detection period, and we rinse and repeat in order to build up the 2D experiment. So we're going to look at a new molecule, trans-2-hexanoic acid. The reason for this is we have a series of resonances, the CH3A, which is coupled to the B, which is coupled to the C, which is coupled to the D spin, which is coupled to the E spin. So what we have is a chain of spin, unbroken chain of spins, mutually J coupled together. If we look at the COSY experiment, as we looked at with the ethyl crotonate, we can see we can find our little squares of pairs of spins. So that was AB, BC, CD, DE, and actually because of the double bond, we can see that C also has a coupling to E. By contrast, if we look at the TOCSY experiment, we can see we've definitely got a diagonal as we had with the COSY experiment, that, as I mentioned before, the magnetization that doesn't move from the spin. But we can look at the cross peaks now. So if I take as my example the CH3 spin, the A spin, we can look and we find there are cross peaks to B, there's a cross peak to C, there's a cross peak to D, and there's a cross peak to E. And this is because our spin lock has suppressed the chemical shift evolution and allows the polarization to propagate down the chain of hydrogens through the J coupling. But this is a single molecule, and perhaps the TOCSY is what we would expect. So we want to present ourselves with more of a challenge. So we'll take a mixture of trans-3-hexanoic acid and ethyl crotonate. If we look at the spectrum, we can see, although some of the peaks are recognizable, we have significant overlap between resonances from the two molecules. In fact, in here, we have the CH3 from the hexanoic acid. That's the BCH2, the C, CH2, and we have the signals from D and E, which are very close together in chemical shift and actually can't be separated. On top of that, we have the CH3 from the ethyl group in the ethyl crotonate. We have the CH3 from the crotonyl group in the ethyl crotonate. We have the CH2 from the ethyl group, and we have the two olefinic signals from the ethyl crotonate. The singlet at the end is the OH from the acid group, but that's not coupled to any other spins. So if we look at the TOCSY for this, initially it looks a little confusing, but if I take the first group of signals here, which is the CH3 for the hexanoic acid, and we draw a line through its cross peaks, we can immediately start to resolve the B resonance. This is the C resonance, and this was the D and E resonances. And there are actually no cross peaks to the ethyl crotonate. Equally, I can choose this signal here, which is the CH3 group from the ethyl crotonate, and we see, as expected, that has a cross peak to the CH2 group from the ethyl group. Equally, I can pick up the crotonyl CH3 group, and we can see its cross peaks to the D and E spins in the ethyl crotonate of the double bond. So we can see here that despite the overlap in the spectrum, we're starting to be able to separate out the different spin systems, but because the TOCSY is propagating down a chain, we're separating out the different molecules and associating which spins are associated with one molecule. One of the downsides of the TOCSY, as with the 2D experiments, is it can be somewhat time consuming. This experiment took 45 minutes. Oh, this was just another coupling. But let's imagine that we can do a selective excitation. So here we're going to choose a single signal using a selective excitation and apply the spin lock, which, having excited one peak, will allow us to transfer the polarization to the other peaks that are J-coupled. So and then we'll collect our FID, which we can analyze. So if we look at the spectrum of the mixture of the ethyl crotonate, and we excite first the CH2 peak from the ethyl crotonate, what we can see is we can see the signal from the CH2, but we also see transfer of the signal to the CH3. We can see, although there are some bumps in the baseline, that we haven't transferred polarization to the other spins. So here we're positively identifying that the CH3 peak is coupled to the CH2 within this. We can excite one of the CH2 peaks in the hexanoic acid, and what we see from that is that actually we're getting polarization transfer to the A, B, D, and E peaks, and so we can identify which of those peaks belong to the hexanoic acid. And finally, we can also attempt to excite that large multiplet that belongs to the crotonyl group of the ethyl crotonate, and we can see that we get transfer to the D spin and the B spin. Although there is some noise in the baseline, we actually think this is due to the spin lock. But what this presents is a way of getting single pieces of information that exist in a 2D spectrum, so particular pieces of information, very quickly using a 1D experiment. So the conclusions are that despite the low frequency dispersion and second order couplings, many spectra that you can collect on a benchtop NMR can be interpreted in a straightforward manner. There are a number of resolution enhancement methods which, given the frequency dispersion, maybe should be used routinely with data from low field spectrometers. But if used correctly, they don't compromise the quantitative information within the spectra. Where there is spectral overlap in mixtures or simply due to the dispersion issues, 2D spectroscopy can help us to separate out the overlapping signals. And the 1D version of many of the 2D homonuclear experiments, these can be used to extract particular pieces of information very, very quickly. So I'd just like to say a few thank yous. Thank you to all of you for listening. I'd like to thank the applications team in Oxford Instruments, Anna Godova, Kevin Knott, Alex Agadulin. The work done on the fats and the meats was done in conjunction with the Institute of Food Research, and that was Kate Kemsley's group, and Marianne de Furnez and Andrew Watson, and some recent discussions with Ryan Mewis and Oliver Sutcliffe at Manchester Metropolitan University. Thank you very much. So Kate and I will now just have a look at some of the questions that have come in, and we'll see what we can answer. So the first question that I've got coming in now, are all of those experiments set up in the instrument by default? All except the newest experiments, which are the 1D selective excitation. They're not set up at, well, they're set up on my instrument and can be set up, but they're not on the instruments as standard. The others, all of those other experiments, plus T1 and T2 relaxation measurements are all available on the system as standard. Sorry, there's a question. Can you send me the presentation? I think this will be recorded, and the MP4 will be available on the web, and I'll talk to, I'm not sure whether the actual PowerPoint is available, but certainly the video will be available. So another question is, how is the instrument shimmed, and how often do you need to do this? We have a set of electrical shims, and we use an automated imaging method to do a full shimming. We can then iteratively shim the X, Y, and Z, the linear shims, and occasionally we do that once a day, but in general, once it's shimmed, if you had a sample in there, it would hold its shim for several days. Okay, there's a question from Marcus Wright, which at some time maybe need to check the E&D assignment in the hexanoic acid. Certainly, we can certainly do that. It's Marcus also asks, do the samples spin? No, there's no spinning on the system. There's no need to spin. Do you have other nuclei set up in the instrument? Yes, you can run, well, as we showed here, you can run fluorine as well as the proton. Does the system have gradients? The system has gradients in terms of the X, Y, Z shims are in fact gradients, and we use these for the image shimming. What we don't have are pulse field gradients for coherence selection. In the preparation of the sample of ibuprofen, is it necessary, is other instrument necessary, for example, a dry bath? No, it's simply dissolved in chloroform. No, is there a flow cell available for online measurements? No, at the minute, we don't have a flow cell. We run the samples, sorry, what range of temperature can you run the samples at? At the minute, we run the samples at ambient temperature. What is a good sample concentration for 1H detection? The experiments that I showed here, especially the 2D, were all between 0.2 and 1 molar. But typically, we can collect a good 1D proton spectrum with about 20 MIGs of sample. To do the 2D, that would require a longer run because we'd need more scans. I'll take one more question if there is another one. Solvent suppression, is solvent suppression available? We've not, well, it's not available in that the selective excitations have not been released, but we're working on using the selective excitations to do pre-saturation. So if someone had a particular experiment they wanted to try, we could probably set that up with a pre-saturation. So at this point, I'm going to I'll ask if any other questions. We'll take one more quick one. Can we resolve more than 2 compounds in a 2D experiment? I haven't tried. That was a first test was to mix the 2 because they were very close together. In theory, as long as you've got, for a 2D, yeah, in theory, we should be able to separate them out. To use the 1D experiment and extract certain information, you're really looking to have at least one peak that is well isolated from the others, so you can excite that selectively. So thank you all very much for listening. It's been a pleasure, and we'll now close the seminar.